Now let's talk about multiple linear regression. So before we had y equals beta 0 plus beta 1 x plus eps. Now we're going to introduce more input variables and still keep one output variable y. So we have y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus ... beta p xp plus eps. And so p is our number of variables, n is still our number of points in the training data set, right? And so we can rewrite this equation in matrix form because that's going to be easier now that we have more variables. So we're going to have two vectors multiplied together and then this eps on the end. So we want 1 times beta 0, and then x1 times beta 1, and then x2 times beta 2, all the way to xp times beta p, right? And so now it's actually a matrix times a vector because this y is a changing for each I. It's an entire column. This x1 is changing for each I. It's the first value for each row. And this is also a column of all ones, right? And of course, this is also a column each I, each row, each point has a different random noise. But when we write it this way, we can easily give this a name x and this the name beta. So beta is a vector of beta 0 to beta p, and x is a matrix of a column of ones, then a column with the first variable, column with second variable, etc. And so then y equals x beta plus eps. That's a pretty simple form for our model, right? And again, the key thing that we're going to find is the parameter beta. So we want to, again, estimate beta using least squares. So that means we're going to take the minimum over beta of the sum of squared error. Yi minus y hat I for each I, same as sum of yi minus xi beta squared. And now our xi, remember, is a vector. We have x1i, we have 1 and then x1i and then x2i all the way to xpi. And our beta is beta 0, beta 1 to beta p, right? So dimension p plus 1 because we have the intercept. Yeah, and then we're going to rewrite this. Instead of using summation notation, we're going to use the norm notation. So this is equivalent to saying y minus x beta 2, 2. So instead of denoting xi as a vector and yi as a single value, I'm denoting y as a vector and x as a matrix. And we're taking the norm. So the 2 norm is the same as doing the sum of squares and then square rooting it. So if we do the 2 norm squares, then it is exactly the sum of squares. If you don't know what this means, that's okay. Yeah, but norm is important when we're doing multivariable math with matrices, right? And so last time we looked at d beta 0 and d beta 1 of our loss function of the sum of squared error, right? Also called the residual sum of squares. Now we have more variables. So we're also going to look at d beta 2 all the way to d beta p. And putting all these together, we can put these together in a vector, and that vector is called the gradient, or grad, of with respect to beta, right? So we can take all these derivatives at once. So grad beta of the norm of y minus x beta to 2, that's going to be, so taking out the derivative with respect to beta, we're going to get the -2 out front, same as last time, because this squared is going to move over there, and this negative sign is going to move over there. And then we're going to have this chain rule, xt, and then y minus x beta. If you don't see that, that's okay. From here, we're going to set this equal to 0, right? That's the same approach. We have a quadratic convex function. To find the minimum, we're going to take the first derivative, set it equal to 0. Well, first, maybe let's show how is this the same as last time. Last time we had dl d beta 0 equals -2 sum of I yi minus beta 0 minus beta 1 xi, and dl d beta 1 equals -2 sum of I yi minus beta 0 minus beta 1 xi. Sorry. But now our x is 1, x1, x2, ... And so we can see that this sort of form, we're putting the 1 up here, the x1 here, x2 next, etc. So these equations are a generalization of the previous linear regression, just with more variables now. And so again, we're going to set this equal to 0, and that's going to give us the beta hat. So for any beta, this is what the derivative, the gradient is. When we set it equal to 0, we've now gotten a specific beta that's the solution to this, and that's the optimum beta, right? And so this is what we call the normal equations. Last time it was just 2 equations, now it's 1 plus p equations. And we'll simplify this first, and then get to the normal equations, right? So multiply -1/2 to both sides, multiply out the xt. So xty minus xt x beta hat equals 0, and then xtx beta hat equals xty. This is how we would normally remember the normal equation, right? That's a little cleaner. And then we can denote the solution by saying beta hat equals xtx inverse xty. Since xtx is always invertible because you're multiplying transpose to itself, it's symmetric positive definite, so always invertible. And this is so important that we give it a special notation, x cross y. So this we call the pseudo inverse of x. X inverse only exists if it's square in linearly independent columns. The pseudo inverse always exists. And yeah, next let's note this the normal equations xtx beta hat xty pretty similar to x beta hat equals y. You're just multiplying xt on both sides. So our solution actually satisfies this system of linear equations, right? This is a system of linear equations just like ax equals to b. except now our matrix is called X, our vector is called beta hat, and our other vector is called Y. And so, I mean, if X was invertible, then very easily we could say beta hat equals X inverse Y. But that's very uncommon that X's can be invertible, because that means we have n equals p plus 1, like X is a square matrix. And like we have the same number of data points as we have variables, and it works out that they're linearly independent, which also like is a bad assumption, right? So that's not going to be very helpful. But what is helpful is if we have other properties of X, like X equals QR, that's going to exist for many more X. So we have a factorization of X that's X equals QR, then X beta hat equals Y turns into QR beta hat equals Y, and then beta hat equals R inverse Q transpose Y. And R is triangular, so it's easy, it's quick to find the inverse, and then you're just multiplying. So if you have QR factorization, doing this computation is way faster than doing this computation. Yeah, and if you're using an iterative method like QR with a shift to find the QR factorization, or even if you're doing direct method like Given's rotation or Householder or Graham-Schmidt, right? You can find QR factorization faster than you can find the linear regression. Combining it together is not always faster, but what is generally always faster is using the singular value decomposition as SVD of the matrix X. So we're saying that X equals U sigma VT for the sigma U sigma and VT that we've already found. And so then X beta hat equals Y turns into U sigma VT beta hat equals Y, and beta hat equals V sigma inverse UY. And sigma inverse is very easy to find because sigma is a diagonal with potentially more zeros to make it the right dimension, but that just means we're taking each element on the diagonal and doing 1 over, and all the zeros stay 0. So that is also like very quick to find. We have to take the U transpose since we're taking the inverse of an orthogonal matrix. Yeah. The next important topic in linear regression is the computational error. So X represents the true numerical value with an infinite amount of decimal precision. And then when you store it on a computer, that turns into 1 plus delta times X, or X plus delta X, because the true value is being rounded, and this small perturbation of X is what actually is stored in the computer. And so the same happens for Y. Y goes into Y plus delta Y. And as you perform more computations, such as matrix multiplication or linear regression, then the error increases as you do more operations. And we want to make sure that the error is still bounded, and that computationally we can get close to the true result for beta, right? So let's let beta be the true result and beta hat be the computed result. So if we're using the normal equations, then beta equals xtx inverse xty, and beta hat is using that equation on the perturbed x and y. right? And so here we have an observed machine precision, which is the maximum of the two deltas, right? So we can call this epsilon, which is going to be the maximum of the norm of delta x over x times the norm of delta y over y. Or we could have some known machine precision that's saying in a single integer, in a single double operation, that's how much potential error there is at most using this machine, right? So what we want to find is the relative error in computation. So this is the error in just rounding off one value at most, and we want to find a bound for the relative error in beta, so the difference between the true and computed result divided by the magnitude of the true result. And to do this, we're going to consider theta, which is the angle between x, beta, and y. So as we said, like when we have beta from this normal equation, that means we're getting the beta from x beta equals y. And if we look at these two lines, y, x beta, and the angle between them, then that's the theta we're talking about. And we can also say the difference, y minus x beta, is called the residual. So our sine of theta is going to be the magnitude of the residual over the magnitude of y. And then to find the relative error, a bound for the relative error, we're going to look at the three cases of theta. One, when theta is approximately 0, that means we have x beta and y approximately in the same direction. So cosine of theta is approximately 1, tangent of theta is approximately 0, and what is the bound in this relative error? Well, that comes down to linear algebra. We have something called the condition number. So, well, that's the condition number squared. Let's say k2 of x is the condition number of x, also called the spectral radius, and that's going to be computed by taking the max singular value divided by the minimum singular value, and that's going to give us an upper bound on the number of operations when doing matrix multiplication involving x. And in this specific scenario, where we have them in the 2, our bound for the relative error of beta is going to be, we're taking the number of operations times the machine precision. So k2x plus k2x times eps. So this is our number of operations here, and then the maximum error per operation is eps. That's the same as saying 2k2x with an epsilon out front. And then our second case is when we have them in different directions and not orthogonal. So 0 is less than theta less than pi over 2, or really pi over 2 times k, some integer. Pi over 2 times k is not close to theta, like we're not close to the same line case or the orthogonal case, which is going to be our third case, right? So our third case is theta is around pi over 2. And so y and x beta are like that. And so in this second case, what is our bound? Well, our cosine is between 0 and 1, tangents between 0 and infinity, and we're going to have two different directions. So instead of k2 plus k2, right, the condition number added together, it's our upper bound is going to be the condition number squared, k2 times k2, right? So less than or equal to eps times k2 squared is our bound in this case. And then in this case, it's unbounded, right? They're completely orthogonal. The linear model would not be appropriate in this case. The x and y are ill-conditioned to this problem, so it's basically less than or equal to infinity, right? And then in this case, we have cosine of x is about 0, right? And tangent of x, theta is approximately infinity, right? So we want some combined expression that is sometimes infinity when we have this ill-conditioned case, is sometimes 2k2x when we have this very well-conditioned case, and other times is a mixture between them. So the important part is just understanding what the combined expression means and why that's a positive, meaning that we always have in this expression for the bound of the computational error in linear regression. And that means like our relative error is bounded. It's not going to explode given the problem xy. We know whether it is well conditioned to linear regression and that the error is not going to be sizable, right? So here we have factor out the eps, and then we have 2k2x, and then we want this to be the case when cosine of theta is 1. So like that will get us there. And then having the tangent theta out front in front of the second term, when tangent theta is approximately 0 up here, then this second term is approximately 0. And the rest of the second term is the k2x squared. And that works out with this one as well. When cosine's approximately 0, this term blows up. When tangent's approximately infinity, this term blows up and the bound blows up. And then there's also going to be some function of f squared that we're not really considering because f is such a small value. When you square it, that gets way smaller. Almost all of the error comes from the first degree term, right? But big O of f squared, just for completeness,